Hi, everyone. For those of you that are on the line for the Latch-up webinar, you're in the right place. If you would, just give us a couple of minutes. We are going to let a couple of other folks catch up to you and get their registrations and get into the webinar room. So if you just give us a couple of minutes, we'll be right back with you. Thanks. All right, everyone, we're going to get started. Hey, thank you for joining us today. This is the Latch-up on High Current Devices webinar from EAG. My name is Aram Sarkisian. I'm the General Manager of the Engineering Science Division here at EAG. I'm going to do a very little bit of talking today, and then I'm going to hand it off to my esteemed colleague, Barry Fernelius, who's going to really give you the bulk of the presentation today. A couple of quick housekeeping items, however. One, you are all currently muted, so there's no, there's a high number of you, and we don't want all of that noise interfering, but we know that people have questions. So we would ask that in the corner of your screen, you should see a Q&A box, and if you type your questions in that Q&A box at any point throughout the webinar, we'll be collecting those, and at the end of the webinar, we've left plenty of time to hopefully address whatever questions you've got, and we'll be monitoring those with our team throughout the webinar and get to those at the end. So please use that Q&A box. The other thing is we take confidentiality and IP very, very seriously here at EAG. So any question you do write in there, know that we may verbalize it to the general audience and let it out there. So if you have specific questions that pertain to you, let's do that offline. We can certainly connect you to Barry and the team and talk through those things. But for more general questions, just know that this is a relatively public forum. Don't ask anything that you don't want to be a public response. Another thing, the recording. This webinar is being recorded. In fact, the recording has already started. And at the end of the webinar, you'll get a link to that recording, so you can take whatever notes you want accordingly, but know that you'll have a copy of this. And then lastly, immediately following this, oh, by the way, that recording will probably get to you in the next 24 hours to 48 hours or so. In addition to that, we're going to be sending out a short survey. That'll probably automatically hit your inbox immediately following the webinar. Please do answer it. It's just a short few questions. It gives us a sense of how we can improve the webinars and also what kinds of content and things you're interested in, so we can keep these up. Without further ado, let's get into it. Okay, just a quick bit about the engineering sciences services. So basically what we have in this division is an entire set of capabilities that provide kind of an integrated service model that give semiconductor and microelectronic companies a path from essentially new product silicon and ICs, new ICs, and all of the new product introduction efforts that they need can be kind of managed and worked through our labs and get them into kind of high volume production or whatever level of production they need to be at. So the kinds of things that fit into that, of course, are test, ATE and development of test programs and ramping up whatever programs they need and getting those to a production ready state. All of the reliability that goes along with that. This includes the early package qualifications and device qualifications. ESD and latch-up testing, of course, is part of those reliability tests and what we're talking about today. So we've certainly highlighted that. FIB circuit edit and debug. So should you need that to make design modifications, tweaks, or get some prototypes in the customer's hands, we've got that under our wing. And then full failure analysis capability. So this enables us to look at any outliers we see in any of these tests, ESD included, where we can dig in a little further and give some insights. And then, of course, we've got a PCB group within that provides all the hardware and can make all the enabling hardware for things like ESD, reliability test, any of those interface boards that are required. So it's a nice ecosystem of services. We're all very proud to be part of it and work here. I've got about 30 years at doing this, and all the various quality systems that line up with various industries that we serve. All right, so a little bit about our speaker today. So I've had the pleasure of working with Barry for, gosh, well over 10 years now. He's a terrific guy. He leads our ESD and Latch-up business. He's got a couple of lab locations, one here in the Silicon Valley, the other in Southern California in Irvine. We both came on around the same time through acquisitions, and Barry has got just a lot of years as an industry veteran, has been on the member of these JEDEC committees, EAG. We continue to be part of these JEDEC committees, and really is the kind of guy that we want leading this, because beyond just running the lab, it's really those insights. And what you're going to hear today is some of the things that we've seen in Latch-up on these high current devices, and some of the problems that his team has encountered, and how they solve those problems, and the things they're able to do for our customers today. So without further ado, I'm going to turn it over to Barry. Thanks very much.
Well, thanks for coming. A little bit of an overview of what I'm talking about today. First, the obligatory section on what is Latch-up, so we know what we're talking about. I'm guessing we're going to have all levels of expertise out there, so we have to touch all bases. An overview of the Latch-up test as described by the spec, which is an idealized sort of Latch-up test. Then we'll be talking about the real-world test constraints that enter into the picture when you're trying to really do the test on real parts. And then we'll talk a little bit about Latch-up on high current devices and what kinds of issues we see with that, and where we bring value. So first of all, what's Latch-up? Well, if you've been around the industry a while, you've seen the CMOS inverter structure many, many times over the years. Lurking inside of CMOS, there are parasitic transistors, which should show up here in pink, and there they are. So when the parasitic transistors turn on, and you don't want them to turn on, but when they inadvertently turn on, high current can flow from the supply, and that is a Latch-up. That's a Latch-up event. And so much current can flow that the device can be permanently damaged if it is allowed to be in that state for a long time. In FA, back when we used to have aluminum metallization, we've even seen things like the silicon aluminum eutectic form, which requires enormous amounts of temperature and enormous amounts of current. So the condition will go away once you power cycle it, but that's the Latch-up condition that we're talking about. So many of these get fixed by layout, and we have some processes that don't show this, like silicon insulator processes, but pretty much as process technologies are getting tinier and tinier, Latch-up becomes harder to avoid. In fact, for some of the technologies out there, it's not a matter of whether it latches up, but it's how badly does the part latch up. So let's talk a little bit about the Latch-up test. First thing that is important about the Latch-up test, which is obvious, unlike the ESD tests that we do, Latch-up is done under bias. That is, the part is powered up. We also want the part to be in a stable, repeatable, and realistic low current state, and we'll talk more about that a little bit later, about how that might be achieved and why that's important. Parts classified as immunity level A, at least 100 milliamps for the I test, or level B, which means it wasn't good enough to be level A. In the past versions of the spec, they had all kinds of different current levels called out and all kinds of complexities. But everybody agreed that it was probably better to just simplify it. Does it meet 100 milliamps or not? We also can do the test as class 1 room temperature or class 2. Class 2, of course, maximum operating ambient or maximum operating case or maximum operating junction temperature. If you test class 2 and pass, I've never seen anybody pass class 2 that wouldn't pass class 1, because for Latch-up, class 2 is the worst case. And so it's recommended to test to class 2 if at all possible. So here's an overview of every kind of Latch-up test that can ever be done. You'll notice at the top it says do an initial functionality test, and at the bottom it says do a post-stressed functionality test. That isn't done on our latch-up tester. That's done in ATE, and that's I'm presuming when I get parts to test for latch-up that you've done an initial functionality test. Hopefully you've done some data logging on the part, and you've given me a part that you know is good. So starting with a part that you know is good, you power up the part and put it in its stable state, and you measure the pre-stress IDDs for all of the supplies. Then you're ready to apply one of the two latch-up stress. It's either a current stress to a single pin under stress, or a voltage stress to a supply group. Then the stress is removed, and we measure the post-stress IDDs and power down the part. I put optional in there because the spec does not require that you power down the part after testing each individual pin, but it's a good idea to do so, because then you know you're going to power the part back up and put it in the same stable state every time. You're in control of it, where if you don't power it down, you might have some leftover junk from the previous test that you don't want. So the tester that we use by default powers down the part after each latch-up test. Finally, after all the pins have been tested and all the supply groups have been tested, we give the part back to you to do a post-stress functionality test. Now, sometimes some people will partition the test where they use a set of samples to do just the current stresses, do another set of samples to do the voltage stress. As long as you cover the full test and test at least 3 units for the full test, then you've met the requirements of the spec. So again, I talked a little bit about the current test and the voltage test. They're really 6 latch-up tests. So there's 2 types of current stresses: the positive current stress, positive I stress, and negative I stress. And we also have the supply over voltage test, which is done on the supply groups. So I talked about those a little bit before. So those are 3 types of tests, but we do each of those in an inputs and IOs configured as inputs tied low, and one with the inputs and IOs tied high. So the result are the 6 latch-up tests that are listed on the slide. I won't read them to you, but 3 tests times 2 different configurations, inputs high and inputs low, results in this. So if you don't see post-stress IDD measurements that indicate that a latch-up event occurred in both the I test and the SOV test, and the devices passed their post-stress functional test, you passed. There's a celebration, the champagne corks pop, and you can move on to the next device. A little bit about latch-up at Eurofins, EAG. Talented engineering staff and Thermo Fisher MK2 and MK4 systems. For the types of latch-up we're talking about today, it's all done on MK4. Because for the high current latch-up parts, these parts are typically too complicated to do on MK2. We have 7 of these MK4 systems in 2 locations, Irvine and Santa Clara, and all of our systems are fully loaded. They're loaded up with the full number of pins, 2304 pins, which is a 48 by 48 array, fully populated. There's 7 dedicated supplies, 256K vector depth. We can do temperature forcing to 125 degrees C, and we have adapter boards for all of these platforms. One last bullet item on here that's really, really important, and I can't emphasize this enough. We have PCB design capability at EAG. The MK4 boards are designed by a group that we have internal to the engineering science division, and these guys have done many, many of them and are very good at it. And they're an incredible resource when you're trying to do latch up on high current devices. In fact, without those guys, I'm not sure we could do it. So in an ideal world, you'd like to be able to have as many supplies as you want and be able to supply as much current on each supply as you want. You'd want no constraints whatsoever. Well, the power supply constraints in the real world are listed here. There's one supply dedicated to the I test, and it's not a perfect voltage source or a perfect current source. It's just a power supply. There's 7 supplies for biasing and stating inputs on the device. For When you're powering up, each supply can have a power up and a power down delay, but you don't have the same kind of flexibility that you've got on ATE. I've had customers say, can we power up 2 of the supplies, apply a vector, and then power up the others? And the answer is no. The system is just not flexible enough to do it. It's not an ATE kind of system. There's also no capability to have a floating supply, that is, a supply pin that acts as a reference ground for another supply. Can't do that on this system either. Voltage is limited to 0 to 100 volts, although typically for all the things that we're doing for these parts are going to be 0 to 10 volts. Current measurements are not very accurate below 1 milliamp, but that's not really a problem because the kinds of things that happen in the latch-up test will cause currents to flow that are larger than 1 milliamp. So the really important constraint are the current limits on the supplies. Can't have more than 10 amps on a given supply, for all the supplies less than 10 volts. Really, before you do any stress, you don't want any more than around 7 amps on a given supply, and no more than 18 amps total from all 7 supplies. And to protect the relay array, we designed the boards to try to limit current on single pins to less than 300 milliamps. Those are the constraints we're working in when we're doing latch-up. Now let's talk a little bit about a low current state. A little slow, okay. Some of the stable low current states include a reset, a sleep, an IDDQ state, or a standby state. All of those have been used, but really stable, repeatable, and realistic, that's why they're in bold, are the most important rather than getting the absolute lowest current. You could go to a lot of work to give me an IDDQ vector that put the part in the absolute lowest current state, but that's probably not necessary. It just needs to be low enough that we can detect a latch-up event if it occurs. And it's more important that it's stable and that we can make it happen every time. Now, as we're going to talk about high current devices, some of these advanced CMOS processes are going to necessitate high currents on core supplies, and the supplies inside of MK4 are not going to be able to do it. And that's where we're going to be talking about external supplies and the funny things that you have to do to make all of that work. So to put the part in that low current state again, I talked a little bit earlier about supply sequencing, so it's good to know how to sequence your supplies. Static preconditioning, there may be a subset of the pins that are always tied high or always tied low, or you might have a simple reset sequence with a handful of pins, handful of states. We can also, though, do vector preconditioning. So any pin on the tester can be used for vector preconditioning. And we can have a vector as long as 256K states and run up to 20 megahertz. It's a good idea, however, to back off from that, to run at 5 megahertz or 10 megahertz if you can. Run in slow motion because it just works better on most devices. We don't have the capability to do loops and other kinds of fancy things that you do with your vectors on an ATE. It has to be a very straightforward kind of vector. And that's sort of beyond, how to set the vector up is beyond the scope of this discussion. But if you have some questions about that later, I'd be happy to talk to you about that. Finally, external components are required on some parts. We don't recommend them unless they're absolutely necessary. They might be required to have a regulated output be in a stable state. And how the external components will affect the latch-up test, there's an entire appendix in the latch-up spec that describes that. And I'm not going to go through that appendix, but just know that in JESD 78E, that's documented pretty well. That's a good place to find out about it. So now into the meat of this, I almost put this at the very end of the presentation, but I put it here. It's as good a place as any. Before you make a latch-up test submission to us, particularly for the first time, it's a good idea to have a meeting with the engineering team at EAG. And it's a good idea to have not only the product engineer, but a representative member or two of the design team. You guys will know more about your chip design than I can ever know. And we can leverage that to be able to get your latch-up test up and running more quickly. After we've talked about what's going to be required, you'll need to generate a latch-up pin list with 1 pin per line, and shows the pin type and the maximum stress voltage values. And we're not going to talk too much about maximum stress voltage in this discussion. That's another, if you have questions about that, we can talk about that at the end as well. Please treat LDOs and regulated outputs as outputs, not as power. And if possible, if you're submitting a preconditioning vector, a great big vector, simulate it on ATE, both inputs high and inputs low, before you give it to me to make sure that it works. There's nothing more disconcerting than getting a vector where somebody says, well, that should work. That can lead to trouble. Also, for each supply, it's a good idea to have an estimate of how much current is supposed to be drawn when the part is properly preconditioned, so we can see if everything's working properly. So this is a little bit of an eye chart, but if you ask for the test request form, it'll have a sample latch-up pin list in it, and you can consult that to get started with your own latch-up pin list. And if you have questions about that kind of stuff, you can always consult any of the folks on the ESDN Latch-up team. Let's talk about high current devices now. So, as you might have suspected, if the part requires more than 10 amps on any given supply, or it draws more than 7 amps on a supply prior to stress, or the total current for the device exceeds 18 amps, you do high power latch-up. That's a requirement, because the tester, you've reached the limits of what an MK4 can do. So the kinds of problems that you run into, first and foremost, power supplies. There's not enough current on the internal supplies to do what you need to do. Typically, for parts that are going to be drawing high current, they're largish sorts of parts. So socket constraints on an MK4 board, you don't want to have a socket that's wider than a 99 millimeters. Why they didn't design it for a nice even 100 millimeters, don't ask me, I don't know. If we need to go wider than that, we have some ways to accommodate it, but it requires some crazy and unnatural things where you're going to be removing pogo pins on the tester and doing all kinds of crazy stuff. We can do that, but we need to know what the socket constraints are for your part. The PC board can't be the same kind of MK4 board that you use for ESD. In fact, you're going to need a separate PC board for the high current latch-up. So it's unfortunate. Really, the kinds of things that make that board work well when you're doing high current latch-up make it not suitable for use when you're trying to do a human body model test. So the two things are at odds with each other. Finally, temperature control. In the case of high current latch-up, you're probably going to need to actually cool the part to keep it at the temperature that you want it. Because with that much current, the part's going to self-heat in a big way. So these are the major problems that we have to solve when we're doing high current latch-up. So here's a simple block diagram. Shows my MK4 tester. We have the custom PCB that designed by our own team, and then the socket and plunger for doing the temperature control. And I'll show you a photo that shows what those systems look like. There's a power supply bank and a power supply controller, and of course the controller that controls the MK4. So the new parts that aren't normally there is the sophisticated temperature control and plunger. That isn't there when you're doing regular latch-up. And the power supply bank and power supply controller, and all of the things required to make that work. So a little bit of a picture show here. This shows the blue box here on the left, upper left, is part of the temp control system. The plunger and socket is shown in that picture that's in the center. And the power supply bank and its computers, the picture on the right. And there's a screenshot and an oscilloscope picture thrown in for good measure, because when you're running external supplies, you need to check them to make sure that all the supplies are coming up synchronized properly. I mean, you're synchronizing external supplies with the internal MK4 supplies, and we set up scope probes so that we know that we've got everything exactly right. So again, what we bring to the table: high current power supplies. We have a power supply bank that has 3 external power supplies. One can supply about 340 amps, and the other 2 140 amps each. We have worked with a few socket suppliers to come up with a type of socket that works for the high current latch up and also works with our temperature control system. We have a bunch of experience designing the PC boards that are required to do this, and that's another added value. We have the temperature control system. You don't have to provide that. We've got it. And we have the synchronization external controller. This is all a software and secret sauce part that I don't want to give you too much detail about. But most important is the engineering expertise and experience with doing this on devices. We've done this for quite a number of customers, and it's challenging, always interesting, but you know, we'd like to be able to do a little bit more of that. That's why we're talking about it with you here today.